Okay, so dear students, welcome to the fourth lecture of probability theory. And I'll start as usually so that I will recall what we did last week. So last week we start to work with so-called random variables. And the random variable, we usually denote it by capital letters starting with X, continuing with Y, Z, and so on, is, from mathematical point of view, a mapping from the set of elementary events to real numbers. We had some examples, for example, X to be the number of spots on the die, meaning that when we consider the set of elementary events omega 1 till omega 6, where omega I means that there I spots on the die when throwing the die for I 1, 2, 3, 4, 5, 6. Then, from mathematical point of view, X is mapping such that for each omega I, it is given the number I. So when we throw the die and there are 3 spots on the die, it is elementary even, there are 3 spots on the die, we will use the number 3. It is the mapping to number 3, and we will work with the number 3, and so on, and so on. So Y could be the number of successes in one trial where success is defined as 6 spots on the die, while failure is defined as less than 6 spots on the die. Then Y is the mapping such that it is equal to 1 when we get 6 spots on the die, and it is equal to 0 for the remaining omegas. And so it is the number 1 or 0 describing the success or the failure, and so on. In this case, we can get only the finite numbers by this mapping, but we can consider something what is so-called continuous, and it is for example, the case where the random variable is something what is continuous, for example, the time. It can be time of waiting for something. We use the time of waiting for a bus, and so on. And, okay, in order to be more precise, I'll describe it. In this way, so for each omega t, it is equal to t, where the capital omega, the set of all elementary events, consists of omega t. T is from some time interval from 0 to capital T. It can be, for example, 10 minutes. And each omega t means we are waiting for t minutes. So here we have 3 examples from last week. We can have, of course, much more random variables. And it means that when you look to the description by words, you can see that, in fact, the random variable can be identified, or you can imagine this random variable to be a random number. Because our aim is to modify the elementary events to some numbers in order we can work with the numbers in the sequel. And the descriptions of our random variables are the following. The general description, which can be used for all random variables, is so-called cumulative distribution function. Sometimes I will use only the term distribution function, which is the function of a real variable u, given by the description that it is the probability of such events whose images are less or equal to u, or just briefly, the probability that the random number is less or equal to u for all u's from real numbers. And it is the general description for all random variables. And then we use 2 types of random variables we will work with: discrete variables and continuous variables. So we will work with two basic types. Of random variables. The first type are discrete. Random variables, meaning that the number of taken values is finite or countable, meaning countably infinite. So when we work with numbers of events, and theoretically the number of events is independent, it is still countable number of events, and because there is a projection with natural numbers. And in this case, the description is given by the probability that x is equal to some concrete values for k, let's say from some index set, which is finite or countable. So, for example, x the number of spots on the die is given by the description probability that x is equal to 1 is equal to probability that x is equal to 2 and so on is equal to the probability that x is equal to 6 and it is 1/6. Or y the number of successes in one trial. I mean still the trial on the die, so 6 spots are mean success and less than 6 spots mean failure. Then the probability of success, the probability of having 6 spots on the die is equal to 1/6, and the probability that there occurs the failure, so it means that the number of spots on the die is less than 6, is 5/6. And the second type are continuous random variables, meaning that the number of taken values is uncountable. And when we have uncountable number of possibilities of taking values, then the probability that such a random variable, I'm still talking about the random variable x, but it is not the x above. Okay, I will talk about the random variable z. Then the number of taken values is uncountable, so it means that the probability that z is equal to some concrete value is equal to 0 for all k from index z, which is uncountable. Now, okay, so we have another description, and the description is given by so-called probability density, which is a function of real variable, and this probability density describes how the probability is distributed among the taken values. So for example, when z is the time of waiting for the bus, and we know that the intervals between two bus arrivals is 10 minutes, then the probability is distributed somewhere between 0 and 10, and there is no probability distributed in negative numbers because the time of waiting cannot be negative, and there is no probability distributed in the numbers greater than 10. Yeah, so the probability is distributed only between 0 and 10. And in this case, we can see that the probability is distributed uniformly, and this probability density is some analogy to the total probability, and total probability is always equal to 1. Yeah? So it means that this area must be analogy to the total probability, so equal to 1. So it means that the function is constant in the value 0.1. In order, this rectangle 10 times 0.1 has the area equal to 1. And in this case, we calculate the probability that the time of waiting is somewhere between A and B minutes is equal to this area. And so the meaning of this density is that the probability that A is between, Z is between A and B is equal to the integral from A to B from this density. And of course, the distribution is not necessarily uniform. It can happen that we know the schedule of the bus, so it means that we are going, or we are planning to come to the bus stop in the time when we expect the bus arrival, so the density can be a function like this. With higher probability, we come to the bus stop so that we wait shorter time, and with smaller probability, we wait a longer time, but still it holds that the probability that the time of waiting is somewhere between A and B is equal to the area below the the curve. So it means the integral from a to b from this function. And it is what we did last week. And now we will continue with characteristics of these random variables. And this expected value is sometimes called mean value, which is the name which I find more precise. I will explain you why. I will start again, as usual, with an example. So let's suppose that we have 4, let's say, balls, and there are numbers on the balls. Number 1, number 3, number 3, and number 5. What is the mean value on the ball or on something? What is the mean value of these 4 numbers? When you calculate the mean value or the average value, then you take all these numbers and you will divide it by the number of these numbers. We have 4 numbers, so divided by 4. And we get the value 3. What we in fact did, in fact, we took all these numbers and we gave them the weight 1/4, because we have 4 numbers or 4 balls in the box. So each ball, each of these value, but I cannot say value because we have the value 3 twice. So each of these ball in the box have the weight 1/4. And in fact, as I said, the value 3 is obtained twice in the box. So in fact here we have 3 times 1/2. And what we in fact do, we take all the values which are taken by the balls in the box. The values are 1, 3, and 5. And we multiply these values by the probability that when we randomly choose a ball from the box, there is the number 1, 3, or 5 respectively. So when we take a ball, the probability that there is the value 1 on the ball is 1/4. The probability that there is the value 3 on a randomly chosen ball is 1/2. And the probability that there is the value 5 is 1/4 again. And this is exactly what is in the definition of expected value of a random variable. When you look to the slide, you can see that when we consider a discrete random variable, then the expected value, which is denoted by this bold x, bold e times x, is given by the sum of taken values multiplied by their probabilities. So in fact, this expected value is nothing than theoretical average. So the average, which is in fact the mean, is the value which we denote expected value. And in this case, it is quite natural to expect that when we take a ball, we will there will be the value 3, because the value 3 is obtained twice more often than the number 1, twice often than the number 5. So then the name expected value is quite natural. But look what happens when we consider x to be the number of spots on the die when we threw the die. In this case, x can be equal to 1, to 2, to 3, to 4, to 5, to 6. So the expected value of x is 1 times the probability there is one spot on the die. The probability is 1/6 plus 2 times the probability that there are 2 spots on the die plus and so on till the end times 6 spots on the die times the probability that it will occur, it is 1/6. And when you calculate this value, you will obtain 3.5. Yeah? And then this 3.5 should be expected value, but I don't know whether you can expect it, but I really don't expect when I threw the die that there will be 3.5 spots. There will be either 3 or 4 or 2 or 5 spots, but not 3.5. Yeah, so therefore, the word expected can sound quite strange, but it is, in fact, its name. So expected value or mean value means the same, and it is, in fact, the theoretical average of the random number. Okay, and in continuous case, it is very similar, because what we do when we use continuous variable, comparing to the discrete case, we replace the sum by the integral. The taken values are taken values x, and the probability that x is equal to the taken values is replaced by the density dx. In fact, it is the meaning of the density. When we have density, then we know that the probability of each value a is equal to 0, because it is the area of this line segment, and the area of line segment is equal to 0. But the probability that we obtain some value close to a is the area of this object. And so in fact, the probability that we obtain something from the interval dA, from some small neighborhood of A, is equal to this area. And so therefore the probability that x is equal to A is replaced by the density dx. So look for more expected variables. So we can calculate the expected value in the case of waiting for the bus when the time intervals between two bus arrivals are 10 minutes. And we do not know the time schedule. Then, as I draw few minutes ago, the density is such a function. It is 0 out of the interval from 0 to 10, and it is equal to 0.1 in the interval between 0 and 10. Then the expected value of z is calculated as the integral from minus infinity to plus infinity from the function x times the density function dx. And in our case, it is the sum of three integrals. The integral from minus infinity to 0 of x times 0, because the density is equal to 0 in negative numbers, plus integral from 0 to 10 from x times 0.1 x, because the density is equal to 0.1 in this interval, plus the integral from 10 to plus infinity from x times 0 dx, because the density is equal to 0 in the interval from 10 to infinity. So, in fact, this integral is equal to 0, this interval is equal to 0, and the integral from constant times x dx is the constant times the integral of x. It is x squared over 2 from 0 to 10. So it is 0.1 times x squared, or 10 squared is 100 minus 0 over 2, and it is 50 times 0.1, which is equal to 5. And it is the expected value or the mean value of the random number describing the time of waiting for bus. In fact, it is not surprising, because when we have the interval between 0 and 10 and the probability is uniformly distributed in this interval, then we can expect that the mean value will be in the middle of the interval. But you can see that when we calculate the expected value using the description, it is really, it gives us really the number 5. Okay, it was the time of waiting for the bus when we don't know the schedule, so there is no time preferred for the time of waiting. But there are some other situations when we are waiting for some occasion which doesn't come regularly, like the bus, but there is no upper limit for the time of waiting. Here we had the boundary 10 minutes, because we know that each 10 minutes there will come a bus. But it can happen that we are waiting for something, I don't know, for an accident, let's say. Or it's too cruel. Maybe we can wait for something not so cruel. So let's say that V is time of waiting for a call. For a call in a call center. Yeah? Let's consider this time of waiting in minutes. And let's suppose that the density is of this form. It is, of course, equal to 0 for negative numbers, because the time of waiting for something cannot be negative. And the description for the positive x is e powered by minus x. And it is quite a reasonable model, because look what happens. The density is equal to 0 for negative times of waiting, and it is such a decreasing function starting in e powered by 0, so starting in 1. And it makes sense because the highest probability is somewhere close to 0, because 1 minute. Sorry, now I told you what is the expected value. So from another side, there is a higher probability in quite a reasonable values which can be taken, and there is very small probability for the values going to infinite. So let's suppose that this is the density, the probability density of the random number describing the time of waiting for a call. The expected value of V is the integral from minus infinity to plus infinity from x times the density dx. And in our case, it is again the sum of two integrals. The integral from minus infinity to 0 of x times 0 dx, because the density is equal to 0 in negative numbers, plus the integral from 0 to infinity from x times e powered by minus x dx. This integral is again equal to 0. The area below this function must be equal to 0. And the integral of the rest must be calculated by so-called pair partes method. What does it mean? It means that one of the functions is denoted as u, and we calculate its derivative, which is 1. The second function from the product is denoted by v derivative e powered by minus x, and we calculate v, which is equal to minus e powered by minus x. And then the integral is equal to u times v, so it means to x times minus e powered by minus x from 0 to infinity, minus the integral of the product of u derivative times v, so minus integral from 0 to infinity 1 times minus e powered by minus x dx. Sorry, this bracket is not there. Now, what happens? When we calculate this term, we use the upper boundary, plus infinity. The limit of the function x times e powered by minus x is equal to 0 in the infinity. Why? Because, I said it just briefly, because the exponential function is much stronger than a polynomial function. Yeah? So this stronger function is equal, or the limit of this function is equal to 0 in the infinity. So therefore, the whole term is equal to 0. Because in 0, we have the term 0 times e powered by 0, so it is 1. So in 0, we have 0 times 1, it is equal to 0. In the infinity, the limit of this term is equal to 0. Okay, and it means that we should calculate the integral of minus times minus, give us plus. So we calculate the integral from 0 to infinity from function e powered by minus x dx, and as we said, it is minus e powered by minus x from 0 to infinity. As I said, the limit of this function in infinity is equal to 0. So we have 0 minus e powered by 0, so it is equal to 1. The expected value or the mean value is equal to 1. Yeah? So it means that in average, we will wait 1 minute for a call. Okay. So that was the way how to calculate the expected values in discrete and in continuous cases. And let's mention some properties of expected values. So first property is that expected value of a constant is equal to the constant. It makes sense because imagine, for example, that we have a special die where on each side we have 6 spots. So when we throw the die, we always get 6. 6 spots, so the number 6. Okay, what is the average in this case? 6, of course. So when our random number is not random, it is just one number, then its expected value is equal to this number, of course. When we have an expected number, expected value of a sum of random variables, and these random variables are multiplied by some constants, then it can be calculated as the first constant times the expected value of the first random number plus b times the expected value of the second number, which makes sense because the expected value is defined as the sum or the integral respectively. And the properties of sums and integrals which exist, of course, and the sum which converges. The property of integral is that we can take the constants in front of the integral or of the sum, and we can calculate the integral or the sum of random variables as the sum of these integrals or sums respectively. And so it follows directly from the definition of expected value. Let's keep the third property and let's focus on the fourth property. When x is a random variable which is non-negative. For mathematical reasons, I write almost surely, but we can forget this almost surely. I explained this term last time, and as I said, it won't be important for us in this lecture. So when we have a random number which is non-negative, for example, the time of waiting, or the weight of something, of an object, the height of a person, and so on. So when we have some non-negative number, which is very often, then its expected value, which is in fact the mean value, the average, must be non-negative as well. And it makes sense when we have only positive times. Then, of course, the average cannot be negative. And why do I mention this property? Because you could see when I calculated the expected value in the case of time of waiting for the call, we had many minuses in the calculation. And it is very easy to make some mistakes, to forget some minus, or to make some other kind of mistake. So when you calculate the expected value of a random number, which cannot be negative, be careful and be aware of the fact that their mean value, their average, cannot be negative as well. And the property 3 is very similar. When we have 3 random numbers and they are ordered, then also their expected values are ordered in the same way. That's all. Okay, so this was the expected value of the random variable itself. And sometimes it can happen that we want to calculate expected value or the mean value of some function, of some transformation of the random number. We have some cubes in a box, and we have 70% of cubes. With the side length equal to 1, and the remaining 30% of cubes with the side length equal to 2. In a box. What is the expected, or better say the mean volume of randomly chosen cube. And so we have a box and we randomly choose a cube and we look. Is it the small one or the large one? What is the we don't care about the side length, which is given, but we care about the volume. So what is the mean volume of the cubes in the box? So let's consider x the side length of randomly chosen a cube, and we know that x is equal to 1 or x is equal to 2. The probability that x is equal to 1 is equal to 0.7. The probability of taking the cube of the side length equal to 2 is 0.3. But as I said, we don't care about the side length, but we care about the volume of a randomly chosen cube. And we know that the volume is equal to the side length powered by 3. So in fact, the volume can be either 1 powered by 3 or 2 powered by 3, which is equal to 8. And the probabilities that we take the cube with the volume equal to 1 is the probability that we choose the cube with the smaller side length. So it is 0.7. Probability that we choose a cube with the side length equal to 2 is 0.3. So the probability that we take a cube with the volume equal to 8 is 0.3. So the expected value of B is 1 times 0.7 plus 8 times 0.3. This one is in fact 1 powered by 3. This 8 is equal to 2 powered by 3. And so in fact what we did, we knew the distribution, the probability distribution of the side length. And when we calculate the expected value of the volume, we took the values which were taken by x, and by the random number describing the side length. We powered these values by 3, and we multiplied them by the probabilities of the smaller and the larger cubes, respectively. And it is the way how to calculate the expected value of some transformation of random variables in general. So when we consider x to be a discrete random number, a discrete random variable, then the expected value of its transformation is calculated as the sum of transformed taken values multiplied by the probabilities of the values xi. So the transformation is applied only to the taken values. Sometimes the students want to multiply or to power or to make this transformation with the probabilities themselves. But no, the probabilities are the weights of the events, of the situations. But the transformation must be done only with the taken values. So only the taken values are transformed and the probabilities are kept. And in the continuous case, when we calculate the expected value, we again replace the sum from the discrete case by the integral. The transform values are transform values, and the probabilities are replaced by the density dx. So the probabilities of taken values as the analogy in the density dx. And that's all. I won't show you the example for continuous case because we will calculate much more of these characteristics later. So I will skip it now, and I will slowly go to the second characteristic we will use in this lecture, and this characteristic is called the variable. So before I define this variable, I will mention some definitions. So the definition I'm talking about is the definition of the moments of random variables. When we talk about the nth moment of random variable, we mean the expected value of x powered by n. And so in this case, when we calculated the expected value of the volume of the cubes, we in fact calculated the third moment of x, because we calculated the expected value of x powered by 3. So in general, the nth moment is the expected value of the nth power of x. And it is used when we calculate some other characteristic. It is just for help calculation in this lecture. Maybe more important or more interesting is the nth central moment. The nth central moment means the expected value of the distance of the random number from its expected value powered by n. And maybe you can imagine the third term, the absolute moment of the random variable, where x minus ex is really the distance of the number from its expected value, how you can imagine it. I will draw it here. So imagine when we threw the die. We know that expected value is equal to 3.5. And when we repeat the trials and we throw the die, then we can obtain 1, 2, 3, 4, 5, or 6. So we threw the die and we obtain 3. Through the die, we obtain 2. Then we have 4, then we have again 3, then we have, 6, then we have 1, 5, 4, and so on. For each trial, or for each result of the trial, we look to this distance. And the mean value of these distances is called the absolute moment. And it could be interesting as the second characteristic describing how wild the random number is, how much it is jumping. But the problem is that this absolute moment, because of the absolute value, is difficult to calculate. It doesn't have nice mathematical properties. And in fact, it is not so useful. So instead of this absolute moment, we use the second central moment as the characteristic describing how wild the random number is. Maybe you can ask the question, why don't we use the expected value of x minus ex of the absolute difference? Because the difference is negative and positive with the same probability. And when we calculate, so just a brief note. When we calculate the expected value of x minus the expected value of x, look what happens. Here we have difference of two, let's say, random numbers. So it can be calculated as the difference of their expected values. So it is the expected value minus the expected value of the expected value of x. But the expected value of x is constant. It is a given number. So the expected value of the constant is equal to the constant. It is some constant a. It is equal to a. So we always get 0. So it is not good characteristic describing how much the random number jump. So therefore, and as I said, the absolute value is crazy to calculate and it has not very nice property, just briefly. So instead of this characteristic, we use the expected value of the square of this distance. It is called the variance, and I will denote it where x from the word variance. You can sometimes meet in the literature the notation dx or something else, but I will keep the notation where x. And what does it mean? In fact, the imagination is not so natural. In fact, it is the mean area of the squares which we construct over the distances of the numbers from its expected value. So for imagination, it is not so natural, but believe me that this characteristic describes how much the random number jump, how it is wild, as I usually say, and it has very nice property when working with random variables in the SQL. So note or remember the distribution, the definition of the second characteristic, which is called the variance. And here, for now, I will skip the covariance, and I will just mention some properties of the variance and the covariance. So I'm sorry, of the variance only. So the first property is the property we will use when calculating the variance of some random variable, because sometimes it can be quite difficult to calculate this term, and it would be much easier to calculate it in some parts. Usually, we have calculated the expected value before, so therefore we want to calculate something more simple. Look what happens. In the brackets, we have x squared minus 2 times x times expected value of x plus expected value of x squared. Yeah? Still remember that this expected value is a constant. So we get equality that it is expected value, and now I will write the brackets. I will omit the brackets later, but now in order you can see exactly what is calculated. So here is calculated the expected value of x squared minus the expected value of 2 times x times expected value of x plus expected value of the expected value of x squared. So it is the expected value of x squared minus, and now look, this is the constant, so it can be in front of the whole expected value. The number 2 is constant, so it can also go here, and it means that we obtain minus 2 times a, the expected value, times expected value of this x. And it is nothing than 2 times constant is constant square. So it is the expected value of x square. And we have plus expected value of a constant square. So this is a square, meaning that the expected value of a square is also a square. Eh? So it is the expected value square. And it means that we have 2 times expected value of x square, the square of expected value, plus the square of expected value. So here we have minus the expected value of x square. So we obtain the relation which is written in the first property, that the variance can be calculated as the expected value of x squared minus the square of expected value. And now I will omit the brackets from here, because this is the usual notation. Yeah, so in order you can use the usual notation, I will omit the square, and when I will omit the brackets, and when I write the brackets, it is in the case when it is not clear whose expected value is calculated. Yeah? So we have the relation which can be used when calculating the variance, expected value of x squared minus the square of expected value. And maybe you will think about whether it is the same or not. No, it isn't. Believe me, it isn't. Because when we calculate, for example, the expected value of the number of spots square, so it means the mean value of a random number given 1 square, 2 square, which is 4, 3 square, which is 9. And so from squares of number of spots, it is not the same as this average square. It is difficult to be aware of this fact from the beginning, but when you think deeply about it, you will find it. Okay. So let's calculate the variance in our classical examples. So for our classical x, the number of spots on the die, we have the expected value equal to 3.5. And when we want to calculate the variance using the first property, we need to calculate the expected value of the square root. Because then we just subtract the square of the square root, the expected value of x squared, because we already have square expected value, and to calculate its square is very easy. So we need to calculate the expected value of x squared. And the expected value of x squared means that we use the taken values squared and multiply them by the probabilities 1/6, which is in fact 1 plus 4 plus 9 plus 16 plus 25 plus 36, and it is 10 plus 20, 30, 91/6. So it means that now I will work with, let's say, 7/2 in order it is easier to see. So 91/6 minus 7/2 square is 91/6 minus 49/4, which is 182 minus 147, so it is 35/12. And now I understand that You are asking for the meaning of this number, but as I said, we will use it later for further calculation. So it is in fact some help calculation, but its meaning, its graphical meaning is what I draw here. When we construct the squares over the distances of the random numbers from the expected value, the mean area of these squares is equal to 35/12. Yeah, so that was the variance in the case of the number of spots on the die. And then when we use, for example, Z waiting for a bus, with the intervals 10 minutes, and we don't know the schedule, so in this case, we calculated that the expected value is equal to 5. Then the variance of Z is again equal to the expected value of Z square minus the square of expected value. We have the expected value, so we need to calculate the expected value of Z square. And since our density was constant, equal to 0.1 in the interval from 0 to 10, and it was equal to otherwise, I will write just briefly that it is the integral from 0 to 10. Of course, it is formally the integral from minus infinity to plus infinity from the density, but these parts of densities are equal to 0, so the integrals consisting of something times 0 is equal to 0. So we will use only, for calculation, we will use only the integral from 0 to 10, transform value times the density. Sorry, for the whole time I wrote 0.1, so I will stay with 0.1. 0.1 dx, which is 0.1 times x powered by 3 over 3 from 0 to 10. So it is 0.1 times 1000 minus 0 over 3. So it is 100 over 3. Okay, and now we will put it to the relation for calculation of the variance. So it is 100 over 3 minus 5 square. So it is 100 over 3 minus 25. So it is 100 over 3 minus 75 over 3. So it is 25 over 3. Yeah? And it is the result. So it is the variance for the random number Z. And again, when we make some statistics, when we measure the times of waiting for the bus, this should be the mean area of the squares constructed over the distance of our time of waiting from the number 5. But as I said, more practical usage will come later when we want to make some transfer, let's say sorry, I can't find the word. When we want to normalize the random variables, as you will see in the property 5 in the slides, in fact. So, yeah, this was the property 1, the relation for calculation of variable. And let's go further to the property 2. So, imagine again that we have a random number which is, in fact, not random, which is a constant. For example, our die, which gives us always 6 spots. Then the variance is naturally equal to 0. Because there is no variance in this randomness. When we have still the same value and it corresponds to the expected value, to the mean value, then the differences of the random number of the results of trial from this mean value is equal to 0. So also the squares constructed over these differences must be equal to 0. And so there are no jumps, no variance, that's it. And when we consider some constant a and multiply the random number x by a, then its variance is equal to a squared times the variance of x. Why? Because imagine the situation that we have some expected value of x, and x is jumping around this expected value. Then the variance is the mean area of these squares which we construct over the distances. And now consider, let's say, twice larger expected value. Then it's expected twice larger values for x. Then its expected value is, of course, twice the expected value of x, and the jumps are twice larger. What does it mean? It means that the square which we construct over these jumps are 4 times larger. So therefore, when we multiply x by some a, so it means that the jumps are a times larger, then the square constructed over these jumps are a square times larger. So it is the property 3. And the property 4 says that when we consider a random variable x, which is shifted by some constant c, but the behavior is not changed, then of course the variance is the same. So when we move everything up, everything plus 5, then also the expected value is expected value plus 5, and everything what occurred in this area will occur also in this region, will occur also in the region on another level, but the variance won't change. Okay, and the last property which I mentioned is the property 5, meaning that we can make from an arbitrary random variable the random variable with 0 expected value and with the variance equal to 1. And everything can be done using the expected value of the variance of x and the properties which we mentioned here. So when we consider z to be x from which we subtract its expected value and we divide everything by the square root of the variance, the expected value of z is equal. The expected value of x minus ex over the square root of the variance. The variance is a constant. It is some constant b, so also the square root of this b is a constant. So we can write it in front of the whole expected value. And we have the expected value of x minus expected value of x. But as we showed before, this is equal to 0. So when we multiply it by arbitrary constant, we get 0 as well. And the variance of z is the variance of x minus ex over the square root of the variance of x. Again, this is the constant, so it can stand in front of the whole variance, but in the square, from the property 3. So from the property 3, we get the equality that it is 1 over the variance of x times the variance of x minus ex. But ex is the expected value of x and it is a constant. So from the property 4, we got that it is equal to the variance x and you can see that it is really equal to 1. Yeah? So you can see that when we make this transformation, that we subtract the expected value from an arbitrary random variable and we divide it by the square root of variance, we always get a random number with the expected value equal to 1 and the variance equal to the expected value equal to 0 and the variance equal to 1. And that's the nice property I was talking about concerning the variance, so we will use it in the sequel. Okay, so that's all for today. Thank you for your attention, and we will continue with the exercise as I wrote you in the message.